Hi, this is a quick video on drawing extended force diagrams or extended free body diagrams for the Torx unit. The first example I'm going to show is a fairly simple one. If you've ever watched some of those videos of people who have trained their squirrels to do all sorts of crazy things to get to the bird seed, the bird feeder, you'll know that squirrels are pretty smart about this kind of thing. So let's say we've got a bowl of bird seed over here. And we've got a seesaw. You're going to see a lot of seesaws in this unit. And it's just a seesaw, a plank on a pivot point. We've got a squirrel. I have no idea how to draw a squirrel, so we're putting a squirrel there, S1. We're putting another squirrel, S2, here. And that's what we've got. We've got food, we've got a squirrel on a plank on a pivot. So it's a seesaw. You can go boop, boop, boop. What we do for extended force diagrams, you take the object that's got all the forces acting on it, it's the long skinny thing, and draw a long skinny rectangle. So there we go. Then one by one, think about what forces act on that object and draw the forces, where they act and what direction they act. So in this case, I've got three things sitting on the plank, which means those three things are pushing down on the plank. I've got the weight of squirrel 2 acting here at the end of the plank. I've got the weight of squirrel 1 acting here, and I've got the weight of the bird seed, let's just do B. Oh, that's bird food, BF. The weight of the bird food. All right, so that's what's acting on the plank, right? And then you stop and you say, okay, does this make sense from thinking about it with conceptual forces? Well, if these are the only forces acting on that plank, this thing's accelerating down, right? So we're missing something. What are we missing? The support force, that normal force. So here we've got the normal force acting up. And is anything else interacting with the plank? Is it touching? Is there gravity we've taken into account? No, we haven't. Oops. The plank. Maybe the plank has some weight too. And we're going to draw that, the weight of the plank itself, right at the center of mass. For most of this unit, we're going to be talking about uniform planks and beams and rods. And uniform means center of mass at the middle. So most of the time you're going to be drawing the weight of an object acting at the middle. If something is not uniform, the problem will tell you. All right, anything else? We've got the things that are touching the plank, 4 things touching the plank. We've got gravity pulling down, the earth pulling down. I think that's it. So this is what a basic extended force diagram would look like. Now this was pretty straightforward because everything was straight up and down. There aren't any angles or x direction forces. So let's try a different one. Okay, so here we've got a wall, and for some reason wall is usually signified by these weird angled lines on something. And then we've got a beam. At the end of the beam hangs a sign. And the beam is also supported by a cable, a wire, going up at an angle, attaching it back to the wall. So let's think about, in this case, what would the extended force diagram look like? All right, what object? Well, the long skinny thing that's got a lot of things acting on it is the beam. So we've got the beam. Now what forces act on the beam? Well, what is physically pushing or pulling on it? We've got the sign. So here is the weight of the sign acting at that back end. We have the cable tugging on it, and so we usually call that a tension, and that's up at an angle. What else here? Well, we've got the weight of the beam itself, and assuming uniform beam, I'm going to put that here. And then it's contacting the wall. So the wall's probably doing something. And often we'll be talking about it in terms of a hinge or a pin there, because it's actually a common way to do these things. So what is that hinge or pin doing to the beam? Now remember, these are the forces the beam feels. If we are the beam, what do we feel from the wall? All right, So imagine yourself the beam. You find that. What do you feel from the beam? I'm sorry, what do you feel from the wall? Well, the wall's probably pushing you out. So I'm going to guess that the force of the hinge, the wall, is going to be pushing this way on me. And I'm probably trying to fall, so I'm also going to guess that the hinge is pushing up on me. Now I'm labeling these FHY, FHX. The force of the hinge in the Y direction, the force of the hinge in the X direction. And it's actually good in this case to keep these separate instead of drawing one force at an angle, because when you need to do your force analysis, remember that the sum of the forces in the X equals 0, the sum of the forces in the Y equals 0. It's already broken up for you. You don't have to break up a vector. And it's also easier if you think about it in terms of left, right, and up, down separately. Now, do I know that the hinge is actually pulling up? Maybe it's pulling down. Maybe this is a really tight wire and it's trying to pull it this way, or maybe this is a really heavy sign and that's trying to pull it this way. Make your best guess. Make your best guess, because when you do the analysis, if you guess the direction wrong, you'll just get a negative sign. No worries. So make your best guess for the direction of things that you're not positive on. I mean, we know that weights are down. Clearly, this cable is pulling up on the beam. Now again, stop and say, does this make sense? If I had said, well, I think the hinge is pulling this way on me. Let's suppose I had said, okay, I have a force this way. The hinge in the X direction, FHX would be that direction. Look at it from the forces perspective. I would have a leftward force. The tension is also pulling this thing to the left. We've got some ups and some downs. There's nothing to the right. This thing would be accelerating to the left if that were the case. So I know that this hinge must be pushing in this direction because it's got to counteract the leftward component of the tension. In terms of up-down, it's a little harder to think about because I have the upward component of the tension and two downs. Which one's bigger? I don't know. I'm just going to make a guess that the hinge is pulling up on the beam. Again, if I'm wrong, I just get a negative sign. So that's not a big deal. So when you're doing this extended force diagram or extended free body diagram, don't stop once you think you have anything. Look at what you've got and say, does this make sense? Or is there an unbalanced direction, which would mean you're definitely doing something wrong, because this isn't moving, it's not rotating. And so we know we have to have balanced forces. And then we're going to do the mathematical analysis to tell us how the torques are balanced out. And that'll tell us actually what the tension is, what these two forces are. That's a pretty common problem that we're going to have. For a certain weight of the sign and the beam, what would the tension be and what would these two forces be? And with these three equations, you're able to do that. So that's just basic overview of how to draw extended force diagrams, and you'll get lots of practice because every problem you're going to need to do this. Good job.